The Arctic region is in essence a sea covered with ice, so yes, the North Pole is basically a chunk of ice floating on water. Now as a result, the surrounding sea maintains a relatively constant temperature at around 0 degrees, though it varies from location to location and the deeper you go. Now, the amount of ice will obviously vary from summer to winter, but as long as there's a good proportion of ice remaining, the surrounding water will maintain a relatively stable temperature. However, ice surveys in the Arctic Circle have shown that the amount of sea ice is getting less and less. Check out this animation. So here's a really interesting animation that allows us to see what happens to the volume per year round from 1980 to around 2020. And it'll go around in a circle, and obviously the distance from the edge represents how much the volume we have. So we can expect to have a greater volume in the winter months and a slightly less in the summer months. But notice what happens over time as we go down. Do you notice that we have much greater ice in the cooler months, certainly in the January and February, and obviously less in the summer months, but every year it's getting smaller and smaller and smaller. Now the concern is that one day we will have a summer where there's no sea ice at all in the Arctic, and this is what's called the Blue Ocean event, and it has major ramifications to the global climate. Now why is that, and what are the physics principles behind that? I'd like to do a demonstration that answers those two questions. So what I have here is a relatively simple demonstration to show you the effect of ice on the surrounding water. Now I have a glass here that is two-chambered, so it's going to be relatively good in terms of insulation. And I have two thermometers connected to my laptop. One is measuring around 25-26 degrees, which is the temperature of the water. And then we of course have the ambient temperature, which is around 30 degrees at the moment. And I'm going to basically also add a heat lamp, so it's going to speed up the process a little bit. And in a moment I'm going to fill this with ice. And what we're interested in is seeing what happens to the water temperature. Now of course you're going to predict that the water will go down in temperature. But what will happen when the water temperature starts to stabilize, particularly in the process while the ice is still in the water? What's going to happen? Can you predict that? And what is going to happen to the temperature when the ice finally is completely melted? And we're going to see that over a period of time. So let me add the ice, and we'll add the heat lamp, and let's see what happens over a period of time, and we'll see a graph being continue to develop as we go along. That should do it. Now let's turn the heat lamp on. So here is our graph. Did you notice the trend that was occurring as the ice melted? So here is where I inserted the ice. Suddenly what happens is there is a huge drop. Now the temperature in the room increased, but my ice water certainly decreased in temperature right down to roughly around 5-6 degrees. Now over here, this glitch here is due to the fact that the thermometer moved during the ice melting, and so it sort of bumped to the edges, and here where close to the edge of the glass. Then what you notice here is that the water temperature stays relatively the same as long as the ice remains in the water. But then we get to a point when the ice has finally melted, and now we start to see an increase in temperature in water again. In fact, as the light continues to shine on the glass, the temperature now is increasing, but this only occurred after the ice has melted. So now back to the Arctic. The fact that the water maintains a relatively stable temperature around freezing point from summer to winter means that as the temperature drops in winter, the seawater will freeze over relatively quickly, increasing the sea ice. But over the last 30 years, we've seen a dramatic drop in the sea ice at a rate that's not been seen before, and I've showed you that earlier. And some models suggest that the Arctic ice could be actually ice-free in summer within 50 years. Now, I'm going to provide some of the links in the description below, so you can see where I've got my infographics from and some of the research papers that I'll be referring to, so that I encourage you to look into that evidence further. Now, like my demonstration, the loss of ice will result in the Arctic sea temperatures rising to levels that they've never been at. And the flow-on effect is that the temperature gained in summer might prevent the water from refreezing in winter. For warm water again to refreeze, it has to lose a huge amount of energy. Liquid water has a high heat capacity, meaning that it stores a very large amount of energy for every degree variation. Then once the water reaches 0 degrees, it has to lose more energy to become a solid. And this is referred to as the latent heat of fusion. Now I have 2 videos that discuss those concepts specifically, and I'm going to put them in the description below. So now let's have a look at it more closely in our example. So here I have my water and my ice in the same glass, and for all intents and purposes we're going to make these the same temperature. I know that the temperature of the water was a little higher. That's simply because this is not perfectly insulated. So we're going to say both are 0 degrees at this point. Now we need to examine 2 situations. The first situation is summer. And in summer, energy is going into the system because the environmental temperature is higher than the ice cap itself and the water underneath because they're not in thermal equilibrium. The other situation is winter. The temperature will be below 0, and therefore, again, we don't have thermal equilibrium, which means we're going to have energy moving out of the system, and that of course will mean we're going to lose energy from the ice and from the water. In summer we have energy going into the system, and we have 2 forms of energy. The first is what we call the potential energy. The second one is kinetic energy. Let me clarify. The potential energy is related to the latent heat of fusion, and that's the energy that is required to change a state, changing the solid ice into the liquid state. Kinetic energy, that's talking about the energy of the molecules as they are moving, and that's related to the specific heat capacity. And that's related to the concept of temperature. So the higher the temperature, the higher the kinetic energy. In actual fact, temperature is a measure of the average kinetic energy per molecule. If we've got energy going into the system, we need to do 2 things. We need to first change the solid water into liquid water before we can start increasing the actual kinetic energy of the water or the temperature. In other words, that's why the ice needs to melt first before we see a rise in temperature. So therefore, if the ice remains, the water stays at 0 degrees. Now in winter, if this is already in this situation, in other words, summer doesn't last long enough or isn't warm enough for all the ice to melt, then the energy that's pulled out of the system will only be the energy in relation to the potential energy or the latent heat of fusion. In other words, my water is already at 0, and therefore you don't need to extract much energy for it to go into ice or solid water. But if the temperature is significantly warmer, in other words, we have no ice whatsoever, now the energy that has to be extracted is the potential energy and the kinetic energy. First, we have to drop the temperature, in other words, to get it to 0 because the water is now higher, and then we need to have it to go to the solid form. In other words, we have energy required to drop the temperature, and we have energy required then to solidify the water. A significant increase in energy, and if the winter isn't cold enough, or if the winter isn't long enough, if the water already is beyond 0 degrees, then it's unlikely you're going to get any freezing at all, and so therefore it will stay in a liquid state. Ideally, we want to always have ice maintained if we're going to have an increase in ice in the winter time. So in essence, once the ice is gone, it's not going to come back. Now, all of this does take time. Just because the ice disappears in a summer season, the surrounding water is not going to increase in temperature so quickly that no ice is going to form in the following winter, at least not initially anyway. The blue ocean event is just that though, the point when the summer season will cause an ice-free Arctic. And it may last a couple of months before the return of winter and ice will come back again. But the concern is that the trend will continue. Longer blue ocean events every season till eventually no ice will form at all throughout the whole year. Now we've yet to see the first blue ocean event. Because there are so many factors at play, it's hard to predict with much certainty when it will first occur. You almost need a crystal ball. Now, some models suggest that we might have a 3-month ice-free Arctic by 2050. Some models think that's quite conservative and some suggest earlier. Although there is still some uncertainty in terms of when this will happen, the data shows that there is a very strong likelihood that it will happen at some time in the future. And the consequences are not pretty. The Arctic plays a crucial role in Earth's climate. Specifically, it acts like a heat sink. That is, it loses more heat to space than it absorbs from the sun. And this is basically due to the ice reflecting the light back into space. Now, this is called the albedo effect. The more ice, the more reflection, and the greater albedo. Let me explain. So what is albedo? Albedo is basically a measure of how much radiation from the sun is reflected back. If we have the sun shining a light down, like so, let's say to the surface of this snow here on the lake, this is in Canada, then a certain amount of that light, or strictly speaking, radiation, because it's not just about light, it's about all forms of electromagnetic radiation coming through to the surface, a certain amount is going to be reflected back. So let's say we have 100% going in and we may get 80% being reflected back. And so we say that this has a high albedo. Now, this albedo can vary depending on the surfaces. So for example, my trees here, I might have again 100 arriving and I'll have maybe 40% is being reflected. And I might find 100% coming in, but reflected is maybe only 10%. So this is a high albedo, this is a medium albedo, and this is a low albedo. Now, if you're reflecting 80%, then there will be some 20% absorbed. In this case, we have 60% absorbed, and over here, 90% absorbed. And that means if that's absorbed, we're going to see an increase in temperature. So if, for example, snow were to reflect back 80%, a small percentage of the energy is going to go into the snow, and that of course could cause the ice or snow to melt. Now, albedo is usually measured as score from 0 to 1. 1 is complete reflection and 0 is complete absorption. This can of course cause problems if the absorption of the energy causes the snow to melt. We're now going to get to a state where the albedo decreases because now it becomes water. It's going to absorb more energy rather than reflect it, which is going to rise. Now, according to Jennifer Francis, a research professor at Rutgers University, the loss of ice and as a result, the loss of albedo has already contributed up to 25% of global warming. Now, like I said, I will put the link to her research in the description below. So if we were to lose all the ice, we will get a runaway temperature rise, a bit like my demonstration. Now, this will have flow-on effects. None of them are particularly positive. There's the melting of the permafrost, which can lead to increased erosion, but potentially can release more greenhouse gases such as methane. A permafrost study published in the Nature magazine in April of 2019 has shown that the Arctic has been 2 degrees warmer than in any other time in the last 10,000 years. Again, I'll put the link in the description below. Now, since weather patterns are influenced by ocean currents and their temperatures, we can expect climate and weather systems to become far more unstable and unpredictable when the ice completely melts. Jet streams are large air currents in the upper atmosphere, and their flow is determined by the cold air mass in the Arctic, and as a result have a significant impact on weather systems. So again, if there's a change in Arctic temperatures, we're going to see drastic changes to these airflows. And then of course, not to mention the loss of habitats for many species that rely on the frozen ice shelf, as well as the aquatic ecosystems that are very temperature sensitive. So again, it's going to have an impact on biodiversity. So how can we prevent this, or at least reduce the chances of it occurring? Well, considering that my focus has been to discuss some physics involved in climate science, I'm going to leave that up to you to look into and act on. I will, however, leave you with this cartoon by Joel Pett, published in USA Today in 2009 at the time of the Copenhagen Climate Change Conference. Well, I hope that's helped you understand the physics behind the blue ocean event and why it matters. Please make sure you like, share and subscribe this video, and make sure you hit the bell so that you always get the latest updates to my videos. In any case, my name is Paul from High School Physics Explained. Bye for now. Too warm.